Hi, my name is Karia Dibert, and I'm a grad student at the University of Chicago working with the South Pole Telescope Group. And I'm going to be talking about the next generation camera for the South Pole Telescope called SPT-3G+. So as Joshua already mentioned, the South Pole Telescope is a 10-meter submillimeter telescope that observes the oldest light in the universe, which is called the cosmic microwave background, or CMB. And the South Pole is the perfect place to observe the CMB because of its uniquely dry and stable atmosphere. There have been several cameras on SPT over the years, but the most recent one and current one is called SPT-3G. It observes the cosmic microwave background at 95, 150, and 220 gigahertz, so at 3 frequencies with 14,000 active detectors. Here's a picture of SPT, and then next to it, here's a diagram from the side, and in red I've circled the 3G receiver, which is this cylinder here. At the end of the 3G survey, this receiver will be replaced with a new camera called SPT-3G+. SPT-3G Plus will observe the same area in the sky as SPT-3G, but at higher frequency. It'll observe at 220, 285, and 345 gigahertz. So that'll provide a high frequency and high sensitivity complement to the SPT-3G dataset. It'll also be an on-sky demonstration of new detector technology because instead of the usual TES bolometers, we're using 34,000 microwave kinetic inductance detectors, or MKIDs, which will be multiplexed at 2,000 per gigahertz. So we'll be able to increase on the detector density and double the detector count of SPT-3G with reduced thermal load in our cryostat from any cold readout electronics. Here are some science goals for SPT-3G+, and this diagram showing the evolution of the universe from the first atoms released of the CMB up until modern-ish times. So back here, there's an effect called the Rayleigh scattering of the CMB, which is when that oldest light, the cosmic microwave background, scatters off of the first hydrogen atoms that form. Detection of this signal would be a probe of cosmic expansion and ionization history around this time, and it's a signal that SPT-3G+ hopes to be a pathfinder in detecting. Later on in the universe's evolution, we have this period called reionization, in which the first stars and galaxies have condensed into dense areas and began to ionize the space around them in these expanding bubbles of free electrons. The cosmic microwave background can scatter off of these free electron bubbles in an effect known as the kinematic Sunyaev-Zeldovich effect. And by measuring this effect with high precision, as SPT-3G+ plans to do, we'll be able to place new constraints on the time and duration of this reionization period. Finally, or not finally, second to finally, we'll be able to look at some of the first galaxies and protoclusters that formed in the universe and look at the dusty emission from the star-forming regions of these galaxies. And so we'll be able to look at how they formed and how these old galaxies evolved to the point that they're at today. And then finally, we'll be able to expand our cluster finding survey to even higher redshift than before and find new clusters via the thermal Sunyaev-Zeldovich effect at higher redshifts due to SPT-3G+'s high frequency bands. In addition, we'll also be characterizing the cosmic infrared background, which serves as a foreground to some secondary CMB anisotropy detections. So we'll be able to help subtract that. We'll be measuring over the summer galactic survey dusty emission from our own galaxy, the Milky Way, including polarized dusty emission. And we'll also be able to make submillimeter measurements of the transients that we've already detected with SPT-3G, including gamma ray bursts in asteroids, which will add to our spectral information about those events. The instrument, or the receiver that I pointed out in the first slide, will be replaced with this design here, this cryostat here, in which it works by the light coming in from the top after reflecting off of SPT's main mirror system, down through these individual optics tubes of lenses onto the detectors, which are shown by these hexagons here. Now the detectors operate at 100 millikelvin, which is only a tenth of a degree above absolute zero. So the whole system is cooled down by a dilution refrigerator shown right here. The optics tubes are all independent. There's 7 optics tubes, of which you can see 4 here, and this allows for individual tubes of detectors to be upgraded throughout the survey as needed. The detectors themselves are shown in more detail at the bottom of the slide. So each of these hexagons is one of the 7 wafers of detectors that'll be on the telescope. And in this schematic of one wafer, I've pulled out a zoom in of one triangle, so one sixth of one wafer, which is shown here. And this is a real picture from the UChicago clean room of these detectors. They'll be read out via this ICE system modified for MKIDs. And you can see an example of that readout here, where one spike or one resonance here corresponds to one detector on the focal plane. And these detectors in lab, these prototypes, have demonstrated the desired microwave and optical performance that we want for SPT-3G+, which is good, and we're now scaling up to making full arrays of detectors. So yeah, and each triangle is read out, has about 1,000 detectors read out by one wire, so we'll only need 42 wires for the entire focal plane. And this is going to allow us to have the high density and the high sensitivity that we need to achieve all the science cases I showed on the previous slide. So thank you, and I'm looking forward to talking more about SPT-3G+ in the future.